All right, so I'm Karen Ghavram. I'm CEO and Engineering Director of LunarG. I'll try to make up some time here. All right, so today I'm going to, there's a theme here, 10 years since Vancouver. I'm going to be taking a bit of a historical look at the Vulkan API. I have a little bit different twist than Tom had on it, but also the Vulkan SDK. And then I will be closing with some discussion around some of the really interesting technical challenges that we have been solving in the developer tools, which will give you guys some insight as to what it takes to do these tools. So, brief history. So here's a little bit different test. 10 years ago, yes, SIGGRAPH in Vancouver, that's when Khronos called for participation in defining the glNext API. And what was driving it, Tom said a little bit differently, was pretty much viewing the industry that the current APIs were abstraction heavy. OpenGL, I think at that time, was 22 years old. And there was a need to scrape away some of that abstraction, give more control to the applications themselves to control the GPU and CPU workloads. I'm going to fly too. After that announcement, LunarG collaborated closely with Valve. We created the first Vulkan driver on Linux against an Intel GPU. It was called the ILO driver. I have found out that was a daughter of the engineer who did that work. Valve, meanwhile, was porting their Source 2 engine to Vulkan. There was some very early validation layer work going on, and that collaboration between Valve and LunarG provided some pretty valuable feedback to the Vulkan working group on 1.0 as well. Don't do that. Then GDC in 2015, Khronos announced the availability of technical previews of the API, and also some demos were given to some key industry players of the Valve Source 2 engine running on that Vulkan ILO driver. And of course, it launched in February of 2016. I do not like this touchpad. All right, so I'm going to go a little bit on a retrospective here about the Vulkan SDK. So this is the state of the Vulkan SDK today in terms of the developer tools that are available. And there are versions for Windows, Linux, and also for Apple platforms. But again, since it's a 10th anniversary, I thought it would be really interesting to go back and look at the state of the SDK with the Vulkan 1.0 launch up to today. So we're going back in time. So the first SDK we released coincident with the Vulkan API. It was Windows and a Linux tarball only. The only, in the SPIR-V tools repository, all we had included in the SDK was the SPIR-V assembler and disassembler and GLSL to SPIR-V from GL Slang. But it was a pretty limited SDK. It did provide some value. I mean, there weren't a lot of application developers yet. Spec just released. Then in 2017, we added a lot more of the shader toolchain elements, such as the SPIR-V validator, and we also had done some optimization passes in SPIR-V for the size of SPIR-V, added SPIR-V cross, which can do reflection and disassembling SPIR-V back to high-level languages. And we also added the C++ binding, a few other tools like the screenshot layer, monitor layer, the Vulkan installation and analyzer, etc. In 2018 was when, in the validation layer, was the first version of the GPU-assisted validation. And this was needed because now the Vulkan API was introducing bindless into the API, which means there are going to be things that we cannot validate until it's running on the GPU. So we had to have a way to actually validate inside the GPU. So that's what we're calling GPU-assisted validation. This was the year we also created Ubuntu packages because Linux distros were still very slow or very incomplete in terms of what packaging they would include with their distribution. So as we did SDK releases, we started doing Ubuntu packages. Let's see, what else? Oh, it was the very first release of VK config, and also, can't forget, 1.1 was released. 2019, we released the license registry. So who cares about this? Well, it's actually quite valuable. This license registry, by binary in the SDK, will tell you all the licenses and copyrights that are contributing to that binary. And this is actually important for corporations that need to scrutinize what licenses are getting installed into their organizations. 2020, so Vulkan 1.2 released, and of course this was the beginning of the pandemic and the beginning of shutdowns, but it didn't impact LunarG in terms of our productivity. We filled out the shader toolchain by adding the DXC, the Microsoft DirectX shader compiler, and VK config was totally rewritten to set the groundwork for how it has evolved to what it's becoming today. The validation layer got its first implementation of the synchronization API. So this is like almost 4 years after the release of Vulkan. It was a simple implementation, hazard detection just within a single buffer. You'd say easy, right? It was 18 man-months of investment. Validating synchronization is not a trivial task. We replaced the VK Trace VK Replay with the graphics Reconstruct API capture tool that now is becoming very popular. I think I got most of it, and 1.2 launched. 2021 is when the Synchronization 2 API released in the specification. We added support for that in the validation layer, and we also wrote an emulation layer, the Synchronization 2 emulation layer. So this is now the beginning of adding some emulation layers to the SDK. 2022. Okay, now in the validation layer, we've added some more synchronization. This is validation within and between queue submissions and across queues. So we're beefing out the functionality. There's still a lot more to do, I can tell you. That investment was another 24 engineering man-months to get that synchronization validation completed. With the release of 1.3, we also released the profiles tool set. Very important tool set. We use it heavily in regression testing in our CI. Lots of application developers use it to sort, filter, get the class of devices that they wanted. We started including Sasha's GPU info, his hardware capability viewer in the SDK that helps promote more uploads to his database of what configurations are being used out there in the industry. Arsenide's Vulk, the meta loader for Vulkan, and AMD's memory allocator. I think I got them all. We've been busy. Come on, mouse pad. There we go. All right, in 2023, the shader object, EXC shader object released. We added validation for that in the validation layer. And as well, the shader object emulation layer was added to the SDK and to the emulation layers or the extension layers repository. Okay, new, as of a week ago. And after me, Jeremy will talk about this, we released the crash diagnostic layer. So we do surveys every year to the ecosystem. I suspect many of you guys may even be doing answers on this survey for us. A theme we hear over and over again is debugging, hung GPUs, device lost errors. It's just really hard. We need a tool. Vulkan API has been adding extensions to help with this. Tom mentioned them in his presentation. We're leveraging those to bring a layer to help debug in these situations. And Jeremy will tell you a lot more about it. Very important tool, I believe. And also new, last week, we also released a new platform. We now have a Windows on ARM SDK. The demand for an SDK for this platform was increasing. We see the market share of this architecture growing quickly. The performance of these systems is quite competitive, and we really think it will attract native games. So hence, we thought it was useful to have such an SDK. We have some of these systems in our CI inside of LunarG, and it is quite zippy. The development workflow on this Windows and ARM will be identical to what you've been doing on Windows x86, x64. As usual, this is where you get your SDK, but now I get to put a red box around the ARM64 platform that we have under the Windows box. Downloads continue to be healthy. We're running at about 38,000 a week right now, just for the Windows SDK. Okay, so this is something I haven't ever put in a presentation, but I think it's appropriate to make it more clear. The SDK does not generate any revenue. It all comes from open source repositories. So how is this work being funded? So Valve was the initial sponsor and what I call the benefactor of the Vulkan ecosystem, and they remain a steady and most gracious benefactor of the ecosystem today. Now, benefactor means that they have been investing heavily in LunarG since before the release of Vulkan with the intention of building up a healthy ecosystem. They want the Vulkan API to succeed. It will not succeed without good, healthy developer tools. And they're a benefactor because we will spend engineering cycles on tools that they may not use directly themselves, but if they see it as a benefit to the general ecosystem, they're all behind it. Go do it. So they're not motivated only for their business motivations, but for the general ecosystem health. Did it again. I do not like this mouse pad. Google provides significant contributions to the ecosystem as well. They do a lot of development such as Angle, the GLES 2 Vulkan layer, the shader toolchain. Most of the shader toolchain, they've been very active in the development of that. And in addition, they do provide support to LunarG financially. We do ecosystem work on their behalf as well. And then, of course, we have various amounts of support coming from Samsung, Qualcomm, ARM, AMD, and Meta. So the first Vulkan SDK, as you saw previously, it was quite incomplete, didn't have a whole lot in it. The validation layer implementation was also very incomplete. That said, it was still pretty good and provided some value to the application developers. So back in 2018, the validation layers were about 90,000 lines of code. Today, we're around 730,000, so it's growing rapidly. So part of what drives this growth is the number of VUIDs. If you look at this graph, back in around 2017, there were around 2,500 valid usage IDs. Today, we're over 19,000. Now, for those of you who don't know what a VUID is, in the specification, it is defining how to use that element of the specification correctly. And that's what the validation layers are validating, is these VUIDs. So the yellow line shows the growth of the VUIDs over time as they're coming out of the Vulkan working group and the specification updates. The green line are those that are actually validated by the validation layer. And the blue line is where we still haven't been able to get validation complete. So what you want to see is the gap between the blue line and the green line to get wider. We're going the right direction. So the validation layer today, it's a healthy open source project, and the functionality is robust. We've been able to add the architecture to the validation layers to do the GPU-assisted validation. Again, to validate things that cannot be validated until it's executing on the GPU. And more is going to be moving into the GPU due to the nature, the bindless nature of the Vulkan API and things I see coming in the pipeline. And we've also added synchronization validation, which I had talked to a bit previously. 2019 was the hazard detection within a single buffer, 18 man-months of effort. 2022, we released the next revision between queue submissions and across queues, another 24 man-months of engineering effort. These two versions enable baseline functionality, but it doesn't cover all the extensions yet, so there's still more to do. We've invested quite a bit inside LunarG in our CI test farm. So the validation layer, it is true, a good portion of the code base can be tested with a software implementation we call the mock ICD in the cloud. But as you've been hearing, more and more validation is moving onto the GPU. And so without actual GPUs in your test center, you cannot fully test the validation layer code. Now, a test center with a bunch of GPUs presents interesting challenges in itself to manage that. You have multiple OSs. We are testing across Windows, Linux, Android, and Mac. We have multiple GPUs. These OSs have all of their behavioral quirks that we have to deal with. GPUs can get hung. We need to be able to detect that and be able to recover. So there are some challenges in managing such a test suite, but it is necessary to get good coverage on the validation layers. You might ask, well, just do a software implementation of Vulkan and test in the cloud. Well, to create a software implementation and keep it up with Vulkan would be a huge undertaking in itself. But I don't believe any customers out there are going to ship a software-only implementation solution. We need to be testing on real hardware to be testing real customer environments. And we're not done with the validation layer. Vulkan API will always continue to evolve. There will always be a lot of work. Okay, how am I doing on time? Oh, I think I'm doing okay, but I might try to get back a few minutes if possible. All right, so I'll talk about a few cases of technology challenges that we have been dealing with. Some in the past we've solved, some we're dealing with today, and what we see coming down the pipeline, some of the challenges that we'll be working on. So synchronization, I have talked about the Vulkan synchronization API. It's a really difficult API to validate. It requires a lot of heavy state tracking, and that can have a high performance overhead. It impacts the performance of the validation layers. That's why it's not on by default. You have to consciously turn on synchronization validation, but there's always opportunity there that we have to performance tune it. Sorry, I do not like mouse pads. All right, descriptor indexing validation. This was an interesting problem. In the bindless functionality of the Vulkan API, resources are accessed by shaders via objects called descriptors, and they're grouped into these descriptor sets. And only descriptors that are used by a shader invocation are required to be valid. So it's not uncommon. You might find an application that might have 1 million descriptors, but they're only using 10 of them. Well, we had a problem that we were just validating all the descriptors. There was an application that, without validation running, would run at about 100 frames per second, turn on the validation, and it went to a fractional frame per second. Really, really dismal. So what did we have to do? And by the way, Jeremy did this work before he did crash diagnostic layer and many other things, is use the GPU-assisted validation to find the descriptors that are actually used, and then only validate those. So here's another case where the GPU-assisted validation architecture is really important for this API, and to be able to effectively and in a performant way be able to run the validation. Okay, I keep talking about GPU AV, but it causes performance issues. What we do when we're doing the GPU-assisted validation is we instrument the shaders to do the validation on the GPU. Well, the shaders can become bloated, and this can impact performance and pipeline compile times and runtime shader execution. This is actually one of our top technical challenges that we are focused on right now, of how to improve the performance of GPU AV, because we must be able to validate on the GPU due to the bindless nature of the Vulkan API. Okay, I mentioned ecosystem surveys a little while ago. So one of the main complaints we get on ecosystem surveys is it's really hard to figure out what my validation layer error message actually means. Well, a lot of what's driving this is the latency as to when do you actually get the error message. It doesn't happen until the queue submit time. So it could be hundreds or thousands of calls previously that you were doing in your application that actually caused the error. So we're looking at ways of what information do we need to track and keep a hold of, that when it comes time to report that error message, we can give more meaningful information to the user. But that also could have performance impacts. But this is a challenge that I think we need to solve to help make these error messages more useful for the developers to quickly understand what they did wrong. All right, let me briefly mention the graphics Reconstruct tool, because I'm going to talk about a few technical challenges there. So this is a cross-platform API capture and replay tool. It runs on Windows, Linux, Android, and Mac. And it has multiple use cases. We know that we have multiple IHVs that are working with us. They use it to run Vulkan workloads during GPU development. But ISVs also use it to help debug their applications. They can get a capture, debug find out what did they do wrong in their application, or they could also send a repo case to an IHV without having to ship their entire application. We use it heavily internally for regression testing. I'm sure there are other people out there in the ecosystem doing so. We use it to capture real application workloads and then can test, for example, the performance of the validation layers against real workloads. And we know and are actively involved in several projects where it's an underlying engine to create a profiler and debugging tools. So you'll see some more of that in the future. So, graphics Reconstruct. The Vulkan API is very explicit. And this creates a portability challenge because it's so explicit. A capture on one GPU certainly can't just be replayed on another GPU, but sometimes even a driver update on the same GPU could break the ability to replay that capture. But we have conflicting use cases, but they're both valuable. People want the exact API calls in that capture. They need it for analysis purposes when they're debugging or working on their new GPU hardware. Oh, but we'd also like to be able to play those captures on a newer or different GPU. Like, for example, during GPU development, we have a new GPU under development. We'd like to take those existing workloads and run them through our simulators. So those two use cases can be in conflict with each other, and we are in process of identifying methods of storing metadata or translation layers to help with some of these portability issues. So the GPUs, they're no longer graphics processing units, right? I mean, GPUs are designed to be very efficient at processing large blocks of data simultaneously. And so we see them in artificial intelligence, machine learning, lots of compute applications as well. And in fact, less graphics is being done on the CPU. Graphics API calls is being done on the CPU, but rendering complexity continues to exist via GPU-driven rendering. And many workloads are moving onto the GPU. Direct3D 12-work graphs is a perfect example of this. It's a method of providing GPU autonomy, where the GPU can feed itself on work. And the work expansion is dynamically expanding, and it's removing round trips to the CPU. Now, this currently is not available in Vulkan today, but this is a good demonstration of the GPU-centric universe. So the problem for graphics Reconstruct is information that we have available today, because there was a function device call from the CPU, will not be available in the future because everything is dynamically happening down on the GPU. For example, addresses will get baked into capture content. How will we find those addresses? They need to be different during replay. So implications of this GPU-centric universe for the developer tools: compare debugging on a CPU versus a GPU. So CPUs have the instruction set architecture. You can step through the code. But GPUs can be a black box, and they're just intrinsically different. The cross-GPU open source developer tools, they're very useful today, but they do need to evolve for this GPU-centric universe. We see more APIs coming into Vulkan that are becoming more and more GPU-centric. And this is going to require cooperation with the IHVs, the spec writers, and the tool developers to get appropriate hooks into the APIs that will enable debugging tools. So an example hook. Today, there's buffer device address capture replay. So you enable it in the driver during capture with graphics Reconstruct. And when memory is being created, you can query the memory location and then use that same location during replay. The current limitation is that it's not guaranteed to work from one vendor to another. So kind of looking back from when Vulkan launched to where we are today, there in essence is one industry standard Vulkan Desktop SDK. It has wide adoption, strong satisfaction, it's open and free for all developers, and it's cross-platform. And the tools, they are very valuable, and they're providing real value to the Vulkan application developers. And the LunarG purpose continues. We need to evolve these tools for a GPU-centric universe. And that is the end of my discussion.